Talking on, what was it, Saturday? I think so. We were talking on Saturday about proof objects, and this is a very familiar topic from last week, so I'm not going to hammer on it too much today, but there are a few more things to say. So let's quickly review. Last time we looked at some proof objects that are generated as Coq interprets tactic scripts. And then we observed that proof objects are real data. So the Curry-Howard isomorphism is not some imaginary thing. It says proofs are really data structures, and you can do computational things with them. You can apply proofs of implications because they're just functions. If you have a derivation tree, well, that's just a data structure, and you can do things like investigate what's in it and do case analysis on what rule was used to do the final step, or even do induction over the whole thing. And this is a completely familiar thing from the kind of proofs that we do informally in programming languages. This is proof by induction on derivations. And then the last thing we discussed was this kind of trade-off between computational definitions and inductive definitions of certain concepts. And the observation was that for some concepts, there's a choice, and kind of either way works, and in fact it's often useful to do it both ways and show that they're equivalent, because then you can have the benefits of both for the modest extra cost of an equivalence proof. But however, that for some concepts only the inductive proof really works because it's awkward or impossible to fit the natural definition of that concept into a obviously terminating computational presentation. Here's one last thing we can do with evidence. We can do inversion on it, and this is also something that we often do in the kind of proofs that come up in meta theory of programming languages and logics, which is you have some inductively defined relation, like a typing relation or an operational semantics. And you want to do a proof of the form, if such and such is typable, then blah, blah. And the way you do the proof is you say, well, consider all the possible ways that there would have been of proving that that was typable. And now for each of those possible ways, blah, blah holds. So this often comes up, for example, if you're doing an inductive proof where you need to walk over two things. So you have maybe a typing derivation and a derivation that one term steps to another. So you have for those of you who've ever done proofs about, say, simply typed lambda calculus, if you haven't, we'll get to them, but this is just a little preview for those of you that have seen it. Often proofs will be of the form, suppose we have a term and it's typable and it takes a step. So we have now two derivations, one in the typing relation and one in the takes a step relation. Those relations are both inductively defined. So in order to do the proof, we often have to kind of take apart the derivations in lockstep. So we do that by doing induction on one of them, and then for each case of that induction, we need to look at what the possible shapes of the other one are. And this looking at the possible shapes of the other one, kind of tearing it apart to find the substructures that correspond to the substructures of the one that we're tearing apart inductively. This is in a paper proof, you will informally often say, by examining the rules of the definition, we see that the only possibilities are A, B, and C. Or if you want to be a little bit more pedantic, or if your definition is a little bit more complicated, you may actually prove a lemma that says the only possible ways of showing that say a typing derivation of a fact of this form could exist are A, B, and C. So let me say that more clearly. One often proves so-called inversion lemmas, which say, if I have a derivation of typing and the type involved has this form, then only these two rules could have been used to prove it. Those are called inversion lemmas. And the inversion tactic is named that way because it's doing effectively the same thing. It's, we saw it first for use only with equality statements, but actually it does something much more general. It says, take a fact, take a hypothesis, whose type is some inductively defined proposition, for example, equality, but other ones as well, evenness, beautiful, gorgeous, typing relation, whatever. And consider all the possible ways that that fact could have been established by applying a constructor to some data, and generate subgoals for each one. Okay, so here, for example, is a little. Let's go to our Coq window and actually look at this. No, that's not the one I want to look at. Right, so suppose we want to show that if n plus 2 is even, then n is even. How do we do that? Well, we have a derivation by assumption that says n plus 2 is even. And basically what we want to do is say, well, consider how that derivation could have been built. It's a data structure. How could we possibly have put together constructors to build something of that type? So we do that with inversion, and the inversion, as we've seen before, gives us some equalities, things that must have been the case, things that must have been the same in order to correctly apply that constructor. In this case, not a very interesting equality. It just says that n must have been even where, let's see. Actually, I'll show you another trick right now. The problem with inversion is a very powerful tactic. It's useful in many situations, but it has one drawback, which is it tends to generate a big pile of equalities that you don't really understand. So the thing that I almost always do immediately after inversion is to substitute away all of the equalities. And I forget whether we've discussed this one in detail, but there's a tactic called subst that takes all of the equalities in the context where one side is just a variable and rewrites it away. So inversion followed by subst will in some way deal with all of the equalities that get generated. Often the equalities are between two variables, and then it just chooses one. So you can't necessarily quite predict what the names are going to be in what comes out. But what comes out is generally so much simpler that you don't care. So here, well, basically it's reduced what we need to show to something trivial. See, is that all I want to say about this? I think that's all I want to say about this. The point is, inversion takes a piece of evidence and figures out all the possible ways that could have been built. Sometimes, if the evidence is contradictory, if it's something that isn't actually provable, then, as we've seen, it will generate 0 subgoals and immediately prove the goal. Or sometimes, if there are several ways, it will generate several subgoals. In the process, it generates a bunch of equalities, which can be, if you don't want to try to figure them out laboriously, can be dealt with all at once by subst. Okay? So canonical forms lemmas usually get, that term usually gets applied to a slightly different kind of lemma. It's a similar thing, but but it's a little bit more than just look at the ways that this could have been built. It's knowing something about the, well, let's see. Yeah, okay. They're very close relatives to a first and second approximation of the same. The reason I'm hesitating is that inversion lemmas are usually easy to prove just by kind of looking at the definition, whereas canonical forms lemmas are usually deeper properties of the system. Other questions? Okay, new topic, slightly new topic. Propositions themselves, not just the proofs of propositions, but propositions themselves are data structures. And they are things that we can program with. So Coq is very orthogonal in this sense. And so, for example, you can write a function that walks over a list and in some way calculates a proposition. For example, you could have maybe a list of propositions, and you could write a function that folds over the list and forms the proposition that is their conjunction. That's a perfectly sensible thing to do. And in many situations, I hope we'll have time to talk about this, in many situations where you're kind of driving Coq hard, it can be incredibly useful and convenient to not just kind of write down a constant proposition and then try to find proofs of it, but to actually calculate the proposition that you want to prove in a computational way. Okay, so one thing is, it's incredibly important, although I hope this is kind of an obvious point for you, it's incredibly important to keep the distinction between a proposition and a provable proposition. So a proposition is just a claim, and that claim may be either provable or not provable. So for example, 2 + 2 = 4 is a proposition. 2 + 2 = 5 is also a proposition. And so they're both perfectly good propositions. The only difference between them is that one is inhabited and the other is not. Propositions are ordinary data in Coq, of course, at a kind of different level than the data that is the proofs of propositions. But all the same things can be done with them. So we can give names to propositions. So we can, for example, define a name plus fact for the proposition 2 + 2 = 4. And then we can write a theorem that says whose body is, whose type is, if you want, plus fact. Okay, now we can construct use old propositions to build new propositions. We've seen this before, of course, because you can take two propositions and put an arrow between them, and that's a new proposition. But we can also define parameterized propositions like even. So that's a function from numbers to propositions. We can define multi-argument propositions, and we can define higher order propositions. So for example, here are a couple of propositions. Here are a couple of parameterized propositions parameterized on other propositions that might look familiar to you. So this proposition says this parameterized proposition has one instance for each p, where p is a property of numbers, a proposition parameterized on numbers. So for each property of numbers, true for all numbers, p is a proposition, which is true informally or provable exactly when for all n p of n is provable. Okay? All right, last thing in this chapter is induction principles. So, of course, the thing that we were looking at a second ago is a little piece of the induction principle for natural numbers. And indeed, the induction principle for natural numbers is nothing very different from the rest of what we've been looking at. It's just a proposition. In fact, it's this proposition. It says, for all p, if we have a proof of p of the zero instance of p, and if given a proof for the n instance of p, we can build a proof for the n plus 1 instance of p, then p holds for all numbers. Okay, so this is the standard induction principle for natural numbers. And the way Coq works is that when you give an inductive definition, it will automatically generate this induction principle and a couple of other closely related ones. So effectively, this induction principle is an axiom that is generated by the inductive definition. So when you give an inductive definition, what gets defined is the constructors, which are axiomatic evidence for building elements of the inductive type, plus this thing, which is an axiomatic way of pulling apart, an axiomatic eliminator, if you want, for the inductive type. And what that means is that if you want, you can actually get away without using the induction tactic. The induction tactic is just apply of the induction principle. It's doing a little bit more. The induction tactic is doing a tiny bit of bookkeeping about kind of rearranging quantifiers for you. But essentially, all that it's doing is the core of what it's doing is just apply of the induction tactic. So this proof illustrates that by proving a simple fact about multiplication without using the induction tactic, simply by doing apply nat end. And if you work through this proof, you'll see that it's slightly different. It differs in a few details because nat end is slightly lower level than the induction tactic. But basically, it's exactly the same thing going on. Okay, and now I don't want to spend a long time talking about this because there are some details to internalize that are a little bit tricky. It's better to take it offline and just read about it and experiment a little bit yourself. But just to give you a high-level overview, the induction principle that's generated by the inductive definition, of course, corresponds to the inductive definition very closely. So essentially what happens is your inductive definition has several constructors. The induction principle has one hypothesis for each of those constructors. And each of the hypotheses says, okay, given some induction hypotheses, prove a particular case of the proposition that we're proving inductively for that constructor. Okay, so we have a bunch of constructors for each one. So for a given constructor C, it takes some arguments. Some of those arguments will be instances of the same inductive type, right? So for example, with the list constructor, with the list inductively defined type, the cons constructor takes two arguments. One is a number, the other is a list. So the clause, the row in that type for the cons constructor will be of the form, suppose I give you a number and a list, and a proof that your property holds of that list. Okay, so the and a proof that your property holds of will come along with every one of the arguments to the constructor that has the inductive type. So you don't get it for the number, you do get it for the list. And then you're supposed to show that for that constructor, if we use that constructor to build a new list out of that number and that sublist, then it has the property that we're trying to show. So knowing that, that was high level, and you'll need to read it to fully internalize it probably, but at a high level, knowing just the form of the inductive definition, you can read off the induction principle in a very direct way. And vice versa. Given the induction principle, you can go back to the inductive definition. Okay. Any questions? So let's go on then to the next chapter, which is called Logic. And let's look at how the very low-level built-in facilities of Coq can be used to define familiar logical connectives. So the connectives that we've used so far have been basically implication, quantification, and equality. It turns out that equality is definable. We kind of already know that, but we'll see it in detail here. So equality is definable, so that just leaves implication and quantification, which turn out to be the same thing. Right? So both the arrow and the for all are instances of pi types. And indeed the way the arrow is simply syntactic sugar for the special case of the pi where it's non-dependent. Okay, so here's the same silly proposition written three different ways. So the last way is the most natural way, which says if n is beautiful, then n plus 3 is. Notice that intuitively, this piece of evidence is a two-argument function. It takes n, and it takes a piece of evidence that n is beautiful, and it returns evidence that n plus 3 is beautiful. So we could name this evidence. We're not going to use that name on the right-hand side here. We use the name n, but we don't use the name of this evidence in the type of the returned evidence. So, but we could still give it a name. We could call it E, for example. Or we could use the special underscore kind of pseudo-identifier that says, I'm binding a variable here, but I don't care to give it a name because I don't need to use it later. Okay. Important point. We are, of course, using the evidence for beautiful n. We're using the value that's going to be passed here in constructing the value that we return. But the type, but the evidence, the value itself, doesn't occur in the type of the returned evidence. So that's why we don't need it here. Okay, so the non-dependent case of for all is just arrow. And for all is just a notation for pi. So we only have pi.
So what rules are there? Pi introduction, pi elimination, and
The usual pi rules. Yeah. Okay, so how could we define other connectives? Well, here's conjunction. It's pretty simple. Conjunction is an inductively defined type. So given P and Q, and PQ is a proposition with one constructor, conj, which takes evidence for P and evidence for Q and becomes or yields a data structure that counts as evidence for P and Q. And we can introduce familiar syntax in the usual way. And now we can prove things about conjunctions using no extra tactics. So we don't need to introduce any more tactics for dealing with conjunctions. As a convenience, I will introduce one more tactic, which is I find it a little bit annoying to have to remember that the single constructor of the conjunction of the and proposition is called conj. So rather than remember that and say apply conj all the time, I usually write just split. Right, so split says I'm trying to prove a conjunctive proposition. I'm trying to prove P and Q. Split says break it into two subgoals, one for P, one for Q. And split is nothing more than a synonym for apply conj. And then conversely, if I have a conjunctive hypothesis, I can split it apart into two hypotheses, P and Q, by using inversion. Okay, so inversion is your friend in many of these situations where you have inductively constructed evidence and you need to find out how it could have been constructed. That's exactly what we need here. So you say inversion and it gets pulled apart into separate hypotheses for the evidence that must have gone into building the evidence of P and Q. So let's actually do this little proof. Called. So let's show that and is commutative. And let's do it together. So how shall we start? Intros, good way to start almost anything. Okay, so we have P, Q, and we have propositions P and Q, and we have the hypothesis that P and Q holds. So inversion would be a good way to get the juice out of the hypothesis that we have. So inversion H splits H, so it keeps H, but also dumps into the hypotheses the evidence that must have been used to construct H. So we have now P and Q. And now what? Split will give us two subgoals, one for P, one for Q. One for Q, one for P, because we're trying to prove Q and P. And now, apply something. Apply, let's see, we want Q here, so apply H1. That gave us Q, and then apply H0 gives us P, and we're done. Yes. Yeah, so there's I'll show this later on, but since it's come up now, oops. Oh, Philly, come on. There we are. Okay, so if you know that the thing that you're trying to prove is a local hypothesis, you can just say assumption and not bother giving its name. All right, going on. If and only if is just P implies Q and Q implies P. The rest of Software Foundations doesn't make very heavy use of if and only if because in older versions of Coq, if and only if hypotheses were a little bit awkward to work with. So Coq wasn't good at, for example, you couldn't just take an if and only if hypothesis and apply it, and Coq would have to figure out which direction to apply. It's gotten much better, so we're gradually reintroducing more uses of if and only if. You may want to use it more than we do. Okay, what about disjunction? Well, disjunction is an inductively defined proposition with two constructors. There are two ways of proving P or Q, either give evidence for P or give evidence for Q. So there are two constructors, one that takes evidence for P and one that takes evidence for Q. And now the rest of the story is kind of what you would expect. And once again, it's a little bit annoying to have to remember the names of the constructors, which are or underscore intro L and or underscore intro R. Those are the names that the standard library writers decided on. I don't like having to remember those, so I usually use left and right as shorthands. So left is a shorthand for apply intro L, which says intuitively, I'm trying to prove a disjunction. Left says, I want to prove the left disjunct. So to prove, my goal is P or Q. I'm going to satisfy that by proving P. Falsehood is representable in Coq in a particularly trivial way. So this is an inductively defined proposition. It looks funny, but it's a perfectly legal one. It has 0 constructors. So how do we build inhabitants of that inductive type? We don't. And if we're given, by hypothesis, an element of that inductive type, what happens if we do inversion on it to find out in what way it could have been constructed? Well, we always get 0 subgoals. Okay, so inverting false proves anything. Let's have a quick look at this ex falso quodlibet, which means from falsehood you can prove anything you want. And let's see how to prove that. So how would we begin? Intros, thank you. And now inversion. And it's proved. Okay, so pretty easy. And this is a standard thing when you're working with falsehood. It's often pretty easy to prove things, and sometimes a tiny bit puzzling to figure out exactly how to massage it into the form where it's easy. So we'll see this more with negation rather than falsehood itself. This thing that we just proved, ex falso quodlibet, is often useful if you're trying to prove something. You're trying to prove P, and you know that something about your context is contradictory. you can, if you say apply ex falso quodlibet, then the goal changes to false. And false is often easy to establish directly from, for example, a negated assumption. Because what is a negated assumption? Let's look a little further down, and this won't surprise you. Not P is defined to be P implies false. Okay, so if we happen to know, some negated thing, it's often useful for the conclusion to be false, and we can get that from ex falso quodlibet. Okay, let's do one of these exercises too, because it's a little bit interesting. Let's do the double negation one. Yes.
If we don't know the name of a logical constant and we want to see how it's defined, and we don't want to look in the reference manual, is there a way to describe the negated part and the mean part?
Okay, so there are various ways to get information out of Coq about how things are defined. Let me list some of them. So you mentioned a couple. One is to look in the reference manual. The reference manual for Coq, you may already have discovered, is, what's a kind way to say this, has needed some work for a while. So it is, but nevertheless, there are some things that it's quite useful for. So trying to look in it to find out the deep meaning of some linguistic feature or how the type theory works or things like that is completely hopeless. What it is good for is looking for, like, if you think you remember that there was a tactic that does exactly such and such, there's a pretty good index of tactics that you can just look through. If you want to find out what are the variants of a tactic that you're using, like, what does the in form do, what happens when you add an as to it, etc. That's all in the reference manual and it's pretty easy to understand. Or if you just want a more precise explanation of exactly what some tactic that you've seen does, you can find that in the reference manual. Okay, so that's what the reference manual is good for, basically. You can find pretty good documentation of a lot of things just by looking in the standard library. So just kind of getting the source code of the standard library and grepping around a little bit will teach you a lot about how things work. Another good thing to know about internally is this search about command. So if you say to the top level, and there are ways to do this through both of the IDEs, you can give a command, search about foo, and it will find you all of the theorems that have anything to do with foo. And sometimes that's a huge long list and it's not useful, but often it's just a page or two, and then you can just scan through and find the one that you can't remember the name of. And there are more sophisticated versions of it where you can write kind of regular expression, like not exactly regular expressions, but you can write a template that says, find me theorems that have this kind of structure in them. Okay, let's try this little theorem. So let's prove from P not P. So I'll give you intros for free. So we've got P and we want to prove not P. How shall we do it? So I often find when working with, especially at the beginning, you'll find it less necessary to do this later on, but when you're first getting started, whenever I see something involving a negation, I like to just get rid of the negation and view it as an implication involving false. Because then it often makes it clearer what needs to happen. So how would we do that? I almost gave you a hint. So unfold, and what's it called? Not. So unfold not tells us what we actually have to prove. Oh, well, then it's easier to see. So how should we kind of obviously proceed? Just looking at the form of things. Another intros, because what's at the bottom of the screen is a hypothetical goal. Okay, so now we've got a hypothesis that P implies false, and the goal is false. So apply looks like a good way to proceed. So apply H0, and now we need to show P, but we have that as an assumption also. Yeah. And since the proof was just a bunch of intros and applies, the proof object is a very simple lambda term. All right. Inequality is just negated equality, so nothing very fancy there. The slightly fancy thing is existential quantification. This is not too fancy. It's just, in fact, for you higher order functional programming experts, should not be very fancy at all. But it takes a little bit to internalize the definition. So here's the actual definition from the library. It says, so existential quantification, the existential quantifier, is a family of propositions parameterized by two things, by a type and by a proposition parameterized over that type. Okay, so let's pass on to the constructor. So xintro, so the one way of proving an existentially quantified proposition is we have to give two more pieces of data. We have to give a witness, which is an element of the type X, and we have to give evidence that P, the proposition that's being existentially quantified, holds for X. Okay, so looking at the first line, X is the type of the witness. So this is for some number. So X there is number. And then P is the proposition about numbers in which X may occur. So that's the parameterization over X. Yes? Well, so the for all is because the introduction form for the existential quantifier, which is what we're defining here, takes two things. It takes a witness and it takes a proof about that witness. So it has two arguments. Remembering that in Coq there really is only one function space, the pi space, the dependent function space. So those are both. So kind of every argument to a constructor is always a pi. Here we need to explicitly write it as a pi, which we notate concretely as the upside down A. So we need to notate it as a for all because we need its name in the type of the second argument to the constructor. Right? So this constructor takes two arguments, a witness and evidence for that witness of P. And the for that witness part is the reason that we need a for all rather than just an arrow. Other questions? Okay, and then we can define standard notation for existentials using the Coq notation mechanism. And you don't really need to understand exactly how all of this works. There's a little bit of fussing around with implicit argument synthesis and things like that. It's not too important. Just a second. It's not too important exactly how it works. What is important is that it allows us to write existential quantifiers in the standard notation. Yes?
I think it does not mean that the property has to hold for every value of type X, right? But I have to give it as
Correct. Yes, thank you. So this is not saying I have to provide a proof that for all witnesses, P holds of that witness. This is saying that the type of the constructor is, for all witnesses, P of witness implies exists XP. Okay, so the constructor can take any witness as an argument. But in order to apply the constructor, we just need to provide one. Thank you. Okay, so now to introduce an existentially quantified proposition, to make a proof of it, we can use apply. So for example, to prove that statement at the top, we say apply ex intro, the constructor. And now we have to say with witness is 2. Why do we have to explicitly say that? Why can't Coq work it out? It's not in the conclusion. So let's look at the type of ex intro again. So remember, apply just unifies the goal with the conclusion of the thing that you're applying. The conclusion here is exists XP, and that does not have witness in it. Okay, so simply by doing that unification, we're not going to find out the witness. And that makes perfect sense because the witness, just intuitively, is something that has to be carefully figured out and may be hard to figure out. So we wouldn't expect unification to just automatically, magically derive it. Okay, so we say apply ex intro, explicitly giving the witness. The unification mechanism works out the type X and the proposition P that we're dealing with, but it can't get the witness. As a shorthand, instead of saying apply ex intro with witness equals, you can just say exists witness. So exists E means the longer thing above. And this is one place where the typesetting of the HTML version of the notes is a little bit awkward. So it's just doing simple string replacement. So unfortunately, that exists tactic also gets typeset as backwards E. Sorry about that. Okay, and then conversely, if we have an existential hypothesis and we want to use it, how do we get the juice out of it? Inversion. Same way we get the juice out of any inductively defined proposition. So if you have an existentially quantified thing, you can say inversion, and that will dump into the context a variable called witness and a proof of P for witness. Usually, having it named witness is kind of awkward. So this is a case where I always use the with variant of inversion, the as variant of inversion to explicitly choose the name of the variable that's going to be the witness. Okay? Equality, we've seen in Bob's lecture, and basically what happens here is pretty much the same. So equality is an inductively defined type. I'm calling it EQ prime here just to distinguish it from from the one that's built in. But this is the definition. This is the built-in definition. So, so EQ is an inductively defined proposition. It has one constructor called REFL equal. And okay, there's one subtlety here that I should explain. If you look at the first line of the definition of EQ prime, you'll see that there's a colon there, and there are some things on the left of the colon and some things on the right of the colon. And this is something that we've seen before, but I haven't explained it yet, so let me do so now. When we're defining an inductive family of things, that family is maybe parameterized over several things in general. And we can place those parameters either to the left of the colon or to the right of the colon. And it means slightly different things. So here is an interesting case because this definition has three parameters, big X, little x, and another little x. Sorry, big X, little x, and another instance of big X, namely the type that things are equal at and the two things that are equal. Right? So the little x and the thing that we didn't give a name to, let's call it little y for the moment, little x and little y are the things that we're saying are equal, and big X is their type. Now, when you put things on the left of the colon, they're called uniform parameters. Why? Because they don't vary from one constructor to another. So for example, in the definition of the list data type, the type X of the elements of the list went to the left of the colon. It's a uniform parameter in the sense that all of the constructors of the list type are building lists with the same type of elements. Okay, so the things on the left of the colon are uniform parameters to the inductive definition. The things to the right of the colon, that is the X arrow, is another parameter, right? Because, so strictly speaking, pedantically speaking, what we're defining here is a family of parameterized propositions of type X arrow prop, parameterized by two more things. So it's a parameterized family. So the first two parameters are uniform, and the last parameter is a so-called is a non-uniform one. What do I mean by non-uniform parameter? It's the thing that varies in, for example, a GADIT, a generalized abstract data type. Right.
But I don't see the difference if you put them on the left or on the right.
Okay, so the difference is two things. If you put it on the left, then you don't have to say it in the types of the constructors. If you put it on the right, in general, you do have to say it in the types of the constructors. Here it happens, EQ is a particularly funny special case. In general, if you have something on the right of the arrow, there's going to be a for all at the beginning of the type of each of the constructors. This is confusing. Let me either make it better or make it worse by skipping ahead a little bit and showing you the simply type lambda calculus. Here is the typing relation for the simply type lambda calculus. Notice that here all of the parameters are non-uniform. Why? Because in different typing rules, in different constructors for this relation, they vary. right? So the gamma, the term, and the type that are being put into this three-place relation by each of these rules are different for each of the rules. So we make them into non-uniform parameters. And now notice that at the beginning of each of these constructor types, there's a for all. Binding, well, all of the ones that we're going to use in the conclusion type, and sometimes some other ones. Does that help? Okay. Yep.
Is there any in the type theory what's going on here, or is it just syntactic things for what you need to write there?
Exactly. The main difference is in the induction principle that gets generated. So let's see if this is correct. I believe that you can always make parameters less uniform. And so you can always take uniform parameters and move them to the right and add some quantifiers. The effect of that is the induction principle that's generated is going to be more complicated. It's going to have quantifiers in it. Because effectively, if you think about it, the uniform parameters are kind of arguments. If you think about the type of list, for example, where is it? Let's see, in poly.v. Here are our polymorphic lists. Okay, so X is a uniform parameter. That means, intuitively, this is a function from types X to inductively defined families. That means that for each of those inductively defined families, the induction principle doesn't need to do any quantifying over X. X is just a constant in each of the induction principles for each member of the family. Whereas if we moved the X to the right-hand side of the colon, then the constructors would have quantified types, and the corresponding clauses of the induction principle would have to mention those quantifiers.
Of course, it makes what we want to prove easier or more difficult, but does it change what we're able to prove?
No, and it shouldn't change what we're able to prove. So if there's a parameter that's uniform, we can move it from the right to the left and get a simpler induction principle from which we should be able to prove all the same things, and vice versa.
Don't we have like a theorem or a lemma saying whenever we have this induction principle, then we can generate the other, and then we don't need to worry about this thing?
So I'm sure there is such a theorem, but it's a theorem about Coq rather than a theorem in Coq. That is to say, in Coq you can certainly witness every instance of that theorem. That is, if you define the inductive type one way and you actually want the induction principle the other way, you can prove the new induction principle from the old one. But Coq isn't going to do that automatically.
So do I have to do it for each instance, or can I just have a theorem?
You would have to do it for each instance.
Okay, so we cannot quantify like overall. So in general, saying something like if I define the inductive type and I have the parameters on one side, then I can generate the inductive principle.
So the thing that you're saying is true. So if I have an inductive definition of this form, then there's another one of this form, and the induction principle for that one follows from the induction principle for this one. But that fact is not internalizable in Coq, I believe.
Question?
Yes?
What happens to the universe levels? What if you move the uniform parameter X to the right?
That's a good question. I think nothing, but we should check. Okay, but let's not check together because I want to. We've spent enough time on this, I think. this is an example. So one thing that I don't like about Coq for teaching purposes is it has quite a lot of these kind of deep waters that take a little bit of type theoretic sophistication to really grasp, and where you actually do need to kind of have a grasp of it in order to be a power user of Coq. You can't get too far without kind of understanding this stuff about uniform and non-uniform parameters and things like that. And it makes it a little complicated for if what you want to do is just get to the point where you can start talking about programming languages, which is the point we're trying to get to. It's a little annoying to have to go through these deepish explanations. However, you will find that even if it's kind of confusing now, things like this will quickly start making sense. And there are a few other things that may take more time, but I'm going to try to sidestep them. Okay, that's enough about equality. I think let's skip to here, relations as propositions. So the last observation to make, and then we really can go on and begin talking about programming languages. The last observation to make is that we've been dealing with propositions parameterized by one thing. Those are properties. We can just as well parameterize propositions by 2 things, by 3 things, by 10 things, and those are inductively defined relations. So here is another slightly interesting inductively defined relation. This is the less than or equal relation, and again, it's slightly interesting because it takes 2 parameters, and it treats one of them uniformly and the other non-uniformly. And the reason for that is simply to get a nice-looking induction principle. So something that you may want to try is changing that uniform parameter into a non-uniform one. You still get a perfectly usable induction principle, but it's a little more confusing to look at. This one is, to my mind, the natural induction principle for less than.
Why define LE? So we have seen that the BLE NAT.
Oh, I see. Yeah. So why not use BLE NAT to define less than as in a computational way instead of the inductive way? We could also do that. And in this case, once again, they're both good. Other questions? Okay, so some programming language stuff. Let's get into a little bit of programming language theory. Okay, so in the 2 lectures yet to come, I want to do 2 little bits of programming language theory to give you a sense of how that's done in Coq. The first one is going to be very simple. We may even get through it in the next 13 minutes. And that is defining the syntax and operational semantics of while programs in Coq. So here are while programs. So this is the world's simplest imperative programming language. It consists of a global memory storing numbers and a set of global variables, so no variable binding or anything like that, just global variables. And then the constructs in the language are assignment, sequencing, conditional, looping, and skip. Right, so that's the whole language. One tiny technical point is that in previous chapters we built up a whole bunch of kind of example theorems that as you go through the rest of the book, would be a little annoying to have to look at all the time every time you say search about. So we've packaged up just the ones that we actually need going forward in a library called sflib. And sflib doesn't depend on all the previous chapters. So from now on, we'll just be depending on sflib, not on logic and all the previous stuff. Okay. So to formally define the syntax and semantics of this little language called IMP, we need to do a few things. So first we need syntax. And for present purposes, I'm only going to define abstract syntax. So I'm going to define syntax trees and completely leave aside the question of how we get from linear strings of ASCII or Unicode or whatever to syntax trees. That's parsing, and I hope it's familiar to all of you. If not, we can talk about it offline, or you can ask your friends. But in formalizing programming languages, we usually skip that step and just talk directly about abstract syntax. Okay, so this is the abstract syntax of arithmetic expressions and Boolean expressions. So the syntax of this language has three layers. There are numeric expressions, and then there are Boolean expressions built over those that get used in conditionals and so on. And then there are commands, which are the actual programs. So arithmetic expressions, there are, for present purposes, four kinds of them. There are constant numbers, and then there's plus, minus, and multiplication. So this is really just using the data type mechanism in exactly the way that you would do in using Haskell or ML or Scheme or whatever in building a compiler. Boolean expressions, same thing. In a couple of clauses, a Boolean expression involves an arithmetic expression, and this is just exactly what you expect. And just for comparison, this is the more standard notation, from which the abstract syntax can be read off very directly. Okay, now we need, let's come to commands in a minute. We need an evaluation relation. And there's going to be two ways to do it, and I'll show you both ways. We can do it computationally, because evaluating an arithmetic expression is certainly a terminating operation. So we should be able to write a fixed point to do that. There it is. And we can also define it as an inductively defined relation, which we'll come back to later. Okay, so here's arithmetic expressions, Boolean expressions. And now we're going to pause for a minute because, well, sorry, not quite ready to pause, but in a moment we'll pause. Before we pause, here's the example that motivates the pause, which is, here is an incredibly simple, the world's simplest optimizer. So this is a function that takes an arithmetic expression, returns an arithmetic expression, where the interesting clause is the second one. If we add 0 to something, it will throw away the 0 plus and just yield the something. Okay, so this is doing a very trivial optimization on arithmetic expressions. And now the interesting thing is to prove a theorem that says that the optimization preserves evaluation behavior. This is the obvious theorem that you would expect, showing the correctness of the optimization. Okay, so the interesting thing to note is, so here's the proof of the theorem, and it's a little bit annoyingly long and a little bit annoyingly repetitive. You could certainly write it out. It's not a big deal. It takes a few minutes. But once you do it, your kind of itch to hack is going to kick in, because you're going to say, well, that was okay, but I wouldn't want to do it again. And I certainly wouldn't want to do it 100 times, or for a language 5 times as big. So could we automate some of that? And the answer is yes, and that brings us to our last topic for today, which is a little bit more information about Coq's automation features. So now we're kind of taking the gloves off and showing you some of the more powerful facilities for scripting Coq. Okay, so we've seen tactics. Tactics are a special case. They're the constant case of programs which are called tacticals. So a tactical is a kind of higher order tactic. And there are several of them. Repeat, for example, is a tactical that takes a tactic and applies it to the current goal as many times as possible. Okay, so repeat of some tactic will keep applying that tactic until it fails. And it will give you back the goal state, the final goal state, the last time just before it failed. Okay. Another extremely useful one is called try. So try effectively changes failure into doing nothing. Okay, so if you have a tactic that you think might work, but you're not sure, if you just apply the tactic, if you just apply was a poor choice of words. If you just write the tactic and put a period after it, it may fail, and that will cause your interpretation of your proof script to stop at that point. If instead what you want is to try it, and if it doesn't work, just do nothing and go on to the next thing, then you can wrap it in a try, and it will have that effect. So why would that be a good idea? Well, you might be writing a tactic program that's going to be used in a variety of situations, some of which might be appropriate for this tactic, and some of which might need another one. So, for example, if you had a very common situation that was going to come up many times, where one of 3 tactics would do the trick, but it would be a different one each time, you could say try T1, and then we'd need a way of chaining them together. We'll come to that in a second. Try T1, and then try T2, and then try T3. Okay. So now, how do you chain things together? That's semicolon. So T1 semicolon T2 does T1, and then as long as T1 doesn't fail, it's okay if it does nothing, but if it doesn't fail, it goes on and does T2. So the way we would achieve this effect is try T1 semicolon, try T2, etc. Okay, so using try and semicolon, we can crunch down this previous proof because, right, so we can do induction E, and then instead of induction E period, we can say induction E semicolon, and then a string of things separated by semicolon to try on each of the induction steps. Sorry, let me go back because I missed telling you something. So if we take T1 semicolon T2, what happens if T1 generates more than one subgoal? We apply T2 to each one of them. What happens if we have T1, T2, T3 separated by semicolons, and T1 generates several subgoals, some of which generate several sub-subgoals by T2? Well, we'll apply T3 to every one of the sub-subgoals. Okay, so if we do, for example, induction semicolon something, the something is going to get applied to each case of the induction. And in this proof, several of them will just disappear because what happens after the semicolon completely takes care of all of the subgoals of that case of the induction. So what will be left in this case is just two cases, the num case and the plus case. Yes?
So it says the 8 right. So it's just reflexive.
It is.
How
Yeah, so we could have done a little bit more try
so just
to get rid of that case.
rewrites would take care of that.
Sorry?
If we just sprinkled try on the rewrites, then A num would fall out.
Yeah, or maybe just the try that's there, semicolon, try reflexivity.
First, in the case of A plus, you use the simplification in the hypothesis 1, but somehow you knew the proof beforehand instead of doing this because you knew you have to make it.
Yeah, so how did I arrive at this proof? I wrote the explicit one first, and then I crunched it down. And this is something that you'll get a feeling for as you go along. But at the beginning, I recommend first writing out the fully explicit thing, and then going back and trying to crunch it a little bit. You may find kind of halfway through the explicit thing that you're beginning to see the structure, and then you can go back and already put in some tries. But once you start crunching things down, it can be a little bit difficult to understand what's actually happening in your proof. So it's better to write it out in the way that you understand, and then figure out what crunching needs to happen to make it short. Okay, there is a more general form of semicolon where instead of the thing after the semicolon being applied to every subgoal, you give a different thing that happens to each different subgoal. So there it is for the sake of reference, but it isn't actually used all that much. The simple semicolon form is the usual one. Okay, let me show you one more thing. We can define names for strings of tactics, and we can parameterize them. So we can write tactic functions. And here is a simple use of that facility that I find incredibly useful in doing slightly larger proofs, as we're now beginning to do. So up above is a tactic called simple and try, parameterized by a tactic C. Okay, so it does simple and then it does try C. Okay, so that's a simple example. Here's a slightly more interesting example. It's called AEXP cases. It's unpronounceable but useful. And it takes two things. It takes a tactic and then an identifier C. What does it do? It does the tactic, and then it does, so semicolon, and then it uses the more general form of the semicolon to do case aux C, and with a different string in each of the cases generated by the first. So typically, first will be induction on some piece of data of type AEXP. Then there will be 4 clauses in the inductive proof. So first does the induction, which splits it up into 4 clauses. And then after the semicolon, each clause has a different tactic executed at the beginning of it. What case aux does is the same as case, except that, well, so if C is the string case, then case aux C is exactly case. If case is the string, if C is the string S case, then case aux C is exactly what S case does, etc. So this C here is a little bit of extra parameterization so that this AEXP cases can be used both at the top level for an outer case analysis or inside of some other case analysis for a subcase analysis and so on. And so at whatever level it is, I'll show you a use of it in a second, that will make it clearer. At whatever level it is, it's basically inserting the cases at the beginning of the corresponding subproofs. So, for instance, I can do AX cases, induction E case, and what that will do is it will leave me with 4 subgoals, one for each of the cases of AX, but each of those subgoals will be labeled in the way that the case tactic labels things. Why is that good? It's good because I can do AX cases, induction E case, semicolon, and then a bunch of things that are going to knock out some of the cases, the easy ones. And what's going to be left are just a few cases. And now so after the period following the induction, when I get dumped into now you need to prove this subgoal mode, I'm going to have a string in the context that tells me which subgoal I'm in. And this is incredibly useful. Right, this is very important for helping you stay oriented when you're doing a big, complicated, semi-automated inductive proof, because it means that you always know, oh, now I'm in this case, and by the way, when you finish with this case, you notice that the string changes, and now you know, now I'm proving different case. Moreover, the case tactic that we already defined all the way back at the beginning does something a little bit special that is incredibly useful, which is, so notice that the AX cases is going to insert a string into the context of each of the subgoals. Here, this case also inserts a string into the context of the subgoal. Right? So this is what we've seen all along. But if there's already a string there, it has the effect of checking that what's there is what we're inserting now. Okay, so why is that useful? Well, suppose that I get the try stuff a little bit wrong, or I change my definition and I reorder the cases, and now I try and rerun this proof. Instead of just some tactic failed in the middle and I have no idea what happened, I will get a failure from this case tactic that says you aren't proving the subcase that you think you are. Okay, so this is why this is an invention of my student Aaron Bohannon, so I'm proud of it. It makes big proofs about complicated definitions much less painful. Okay, time to stop for this morning. So we've been through the rest of the prop chapter, the logic chapter, and the beginning of the IMP chapter. The beginning of the IMP chapter is, there aren't really such interesting exercises yet, but you'll find some exercises in the other 2 chapters, and we'll continue on from where we stopped tomorrow.